I'm ready, doctor.
Okay. So shall we start today with the complex function integration? Okay. Yes, if I'm asking you to integrate z squared, right, from 1 plus I to 2 plus 3I dz. This is exactly, you will go through it like a definite integral of a real function. So yes, when you have a power, you add 1 to the power and divide it by the new one, and you got your lower and upper limit, and then you just substitute by the upper one minus the substitute of the lower one. You know how to find 2 plus 3i to the power 3. You are not going to expand it using the binomial theorem. No, you have to have the magnitude of 2 plus 3i. I call it R1, for example, and you know this is 2 squared plus 3 squared. And you have theta 1, which is, you call it the arch of 2 plus 3i, which is tan minus 1, 3 over 2. Okay, and also I'll go for the second one, R2, the magnitude of 1 plus I, which is root square of 2. And theta 2 is the arch of 1 plus I, which is pi over 4. Okay, tan inverse 1 over 1, it will be pi over 4. Once I have this one, I know if I have 2 plus 3i to the power 3, I will have it, the first one, as R1 e to the I theta 1, and then add it to the power 3. Also, I can get 1 plus I to the power 3 is exactly like R2 e to the I theta 2 to the power 3. Once I finish, I'm just have it in terms of cosine and sine, right? Because I know e to the I theta is cosine theta plus I sine theta. This is how to handle the result, okay? And if you'd like to complete it, but at least now you pass the result. Also, if you have integration, sorry, find the integration of e to the z over 2, okay, from I 1 plus I to 2 plus 2i, right, dz, exactly as I have done with the real function, e to the z over 2 over the derivative of the power, and also I'll put and then I'm just substituting by the upper bound minus the substitution of the lower bounds, right? Okay, now I know I can do this one as it will be e to the 2 over 2, so this will be 1 plus I over half, and this is e to the 1 plus I to half. Without thinking, okay, this is half of this one, right? So it will be 1 plus I over 2 over half, so I can do this too. Now I can write this one as t e to the half, e to the half I. I know this is root square e, e to the I half is cosine half plus I sine half. This is how to write e to the I theta. Okay. Finish. So yes, you can go through anything just like this one. Let's go for if you would like to integrate from minus I to positive I for 1 dz over z. Yes, I heard you. You say the integration of 1 over z is ln z. Okay, from what? Minus I to positive I. Remember, what is your positive I and negative I? This is the x-axis. And this is the y. This is if you have minus I, so this is your minus I. And this is your positive I, right? Okay. You can go from minus I to I in this side, okay? Or you can go from that side. Okay, let's go for one side only now. So if I'm going from this one to this one, yep, I know z equal to what? Ln z. Z I can write it r e to the I theta. And I know from the ln properties, this is ln r plus ln I theta, ln theta. Sorry. Ln I ln theta. Okay. Plus ln e to the I theta, if you like to write it like this. Okay. And what's theta? Ln r is the magnitude of z. Okay. If I'm going from here to here, I go for the half circle with a radius 1, so r is 1, so this one will be completely 0. Okay. So this will be 0, and theta will be from minus pi over 2 to pi over 2. Okay. This is how to handle this one. So yes, I will have r is equal absolute of z to absolute of I, which is 1. Okay. So now I know the integration from minus I to positive I dz over z will be ln z. I change this ln z into the Euler with ln 1, which is ln r is equal to 0. So ln e to the I theta, and I know theta from minus pi over 2 ila pi over 2. But if you go anti-clockwise, it's better to have the positive one. So the positive one, instead of minus pi over 3, you take it 3 pi over 2 and substitute minus ln e to the 3 pi. Okay. Also, if you go to the other side here, from this side, you will go from pi over 2 here into 3 pi over 2, right? Okay. Okay, so you will have the other side, the integration in the blue direction will equal to the same, but you start from pi over 2 into 3 pi over 2. If you go in this direction, 3 pi over 2 and pi over 2, right? And you end up with minus pi I, but this one you have pi I. So what is the difference? The difference is the sign. Okay, so remember, when you go this anti-clockwise with clockwise, okay, you will have the same value but with different sign. Okay, this is when you have definite integral, like the definite integral. Let's link our studying of a complex integration, okay, over a closed curve C. So you have a closed curve C here, okay, and you would like to integrate f of z over this closed field with anti-clockwise to have the positive direction. Without thinking, this one will be 0 when f of z, your function, is analytic in a closed curve. They call it closed contour. I will close contour. Contour is the name of a person. Closed contour C, right? So this is the first important thing. So without thinking, if your function is not analytic, is analytic over inside C, so the integration is equal. So, and look at this one. You have no problem, especially when you don't have a denominator, right? So the denominator makes a problem for you. Let's go for the Cauchy integration theorem. Cauchy integration theorem, to be honest, we have a simple case or simple pool, and we have a general case, non-simple pool. Okay, I will let you know what does it mean, simple pool. It means you have integration over a closed curve, and you have your denominator is z minus z naught. So simple z naught is a simple pool because you don't have a power here, and your numerator is a function of z, dz. Okay, and non-simple pool z naught, when you have the same integration over closed contour C, but your denominator has non-simple pool, it means z minus z naught to the power n. Okay, what is the value of the integration in this case? This integration will equal to what? Yes, I hear you. 2 by I times your function f. Yes, the simple pool comes here. Okay, yes, it not. Okay, that's so far so good. So this is a z naught. Okay, so no need to integrate. You know the value once you know the function f of z here, right? Okay, so what is the value of this one? This is a general case, yes. It is better to write here n plus 1. Why I'm writing n plus 1? To have a nice shape for my result, it is 2 by I f n derivative at this non-simple pool over factorial n. Yes, I hear now. Oh, we don't care about the integration now. We are caring about what? Analytic function, right? This is why we start to study the analytic function, right? Easy? Let's go and have some example. Please take a screenshot. How it comes? Take a screenshot, put in the chat, because you will be ready to solve the question now, right? Yes, no need to integration. Yes, I said. Let's go for the example now. Okay. Let's start with example. Evaluate the integration, number one, the integration of e to the z over z, okay, sorry, over a closed curve, okay, absolute value of z, c, this is my c, equal to 1. Okay, and let's have another one. Z squared sine y z over z minus half dz over what? Yes, I have to know the contour. Yes, c is also absolute value of z equal to 1, right? Okay. Last one, integration over a closed interval of cosine z over z cube dz, and also I will have also my c is okay. Now, before we start solving any question, we have to discuss what we have to know. Yes, we have to know what does it mean absolute value of z equal to 1. Yes, I know the magnitude of z is x squared plus y squared under the root square. Okay, equal to 1. Now I square it, so I have what? Equal to 1. So yes, I got this one in math 1. It is what? A circle with center zero and 0 and radius r equal, or a, you can call it a, equal to 1, right? Okay, now we know how to graph this one. Yes, it is a unit circle. I have one here and one here and one here, minus 1, sorry, and here minus 1. I can make it quarter by quarter, right? Yes, I can get the quarter of this one and the quarter of this one, quarter of this one. So I have my circle here. This is my C here. The contour is the most important part here in your solution. Okay, next, what you should know. Yes, I'm checking what's my pool. My pool, the pool Z naught equal to what? What? What is Z naught? Hello? Shabab?
Yes.
What is it not?
1.
Why it's 1? This is why I'm asking you to take a screenshot from this one. Z naught is a ball. Where is the ball here? Z minus Z naught. You have Z only, so it will be Z minus what?
Z minus 1 minus Z naught. 0.
0, right? So, where is the 0? Yes, it is inside, right? So Z naught is inside C. Okay? So I have to add to this one Z naught inside C. So it is analytic. Okay? So this is inside C. Okay, should be inside C. So it is analytic. My ball is included inside, so I have no problem. Okay. So I guarantee the condition of Cauchy is satisfied, right? Okay. In the first one and the second one. Also, if here Z naught is half. Where is half? Half is here. So it is also inside. Here Z naught is 0. It is inside. This is the main point you have to repeat every time in your solution. You have to graph the contour C, closed contour, and then you decided your Z naught inside or outside. Okay? Now, without thinking, I have the solution for I, the integration over C or e to the Z over Z dz will equal to what? Yes, 2 by I. What's my f of Z? E to the Z. I should put E Z naught. What is it not? 0, right? Yes, this is my simple pool, right? So Z naught is 0, so I just have this one, so I have 2 by I finish number 1. Okay? Okay, take a screenshot because we'll go to the next one, or I'm going to delete this one to have a space for a second. Okay, now I know my contour, so I would like to graph it. No need to write this one all the time, just okay. Let's go for number 2. What is it not? It is half, right? This half inside absolute value of Z equal to 1. Okay, so I can go for Cauchy-Riemann integration. So the integration over this C for Z square sine by Z over Z minus half dz equal to what? Yes, I'm hearing you say this is simple pool, so 2 by I. What is your Z? F of Z? It is my numerator, Z squared sine by Z. No, not Z. You have to write Z naught. What's Z naught? It's half. Okay? And here Z naught is half. So you shouldn't write Z naught. I replace Z naught by what? Yes, by half. So I have half squared sine by every Z I replace it by Z naught. Now I finish. So this will equal to what? 2 by I half square is 1 over 4. Sine pi over 2 is 1. So I end up with pi I over 2. Finish? Yes. Let's go for the last one. No need for this one. Now, this one will equal to what? I know Z0 is 0. Z0 is 0. This 0 inside my C, which is absolute value of Z equal to 1. So I can use a Cauchy-Riemann integration. Cosine Z over Z cubed dz will equal to, yes, 2 by I. Oh, don't forget, this is not simple, right? So before you start here, you should mention here, non-simple is not simple. It is of order what? Order 2, yes. Because in my Cauchy-Riemann formula, I have n plus 1. So n will be 2, right? Catch it? So I would like to write here, oops, n equal to 2. So this integration here, I just move a little bit here. Yes. So my third, I choose a nice color. So number 3, I know the integration of cosine z, because z0 is not, I can write it z cubed here, dz equal to what? Yes, 2 by I have my f of z, which is cosine z, and I have second derivative, so I have double dash, okay, and after I finish the derivative, I have to write z equal to z0, and don't forget to divide it by factorial n. N is 2 here, right? So I have to divide it by factorial 2. You are lucky because d by dz for cosine z is minus sine z, and also if you have the second derivative, it will be minus cosine z, right? Catch it? So I have 2 by I, and I have here the double derivative, or the second derivative of this one is minus cosine z, and I have to write z will equal to z0, and z0 is 0 over factorial 2 is 2. Now I have 2 by I minus cosine 0 over 2. This 2 will be cancelled out with this one, so I have minus cosine 0 is 1, so I have minus by I. Catch it? Are you ready to solve one of the following question? Okay. So please stop recording and give yourself time to solve this question. Exercise.